laptop that you have sitting on the desk. So you get to a point where you need to trade off power and size. Okay? And then the second one is dimensional redundancy. So a lot of times when you have a table, you'll have columns that represent the same thing. So instead of using all of them, you can cut off some, or you can combine them somehow, but you need to get rid of them so that you have less work to do when it comes to the actual algorithm. So if you look at this one over here, you have 6 dimensions or 6 columns. First you have goals, shots and chances, and then you have tackles, blocks and clearances. So in this one, you can reduce the 6 columns down to 2, right? You can make some measure for attack and include the first 3 columns. You can decide how you build that measure, or you can have a measure for defense for the other 3, and you can decide how you put that together. Okay, so as I said before, dimensionality reduction is just reducing the number of variables, but you still maintain the information that's in the data set. Okay, so you have 2 ways of doing this. One is feature selection, the other one is feature extraction. So feature selection, all you're doing is you're taking columns directly out of the original data set. So for example, if I go back to this one, let's say all you cared about was the goals and the shots with regards to the attack stat in this case. Then all you do is you just remove the chances column out of your table, okay? And you select the chances, the goals and the shots, right? That's feature selection. So you take the column as is out of the data set and you don't do anything to it. You're literally just removing and adding columns to the original data set. There's no manipulation of the data in any way, okay? Does everyone get that? Then you have feature extraction. So feature extraction is different. So feature extraction, you build some sort of mathematical function or mathematical representation of how you combine different columns together. So you create a new column by combining different columns, and you decide what the mathematical representation of that combination is. Right? You can do that in many different ways, and you're going to see one now, but that's feature extraction. So you have a brand new column that represents different columns within your data set. Do you guys see the difference? No response. Yes. Okay. So another reason why we do dimensionality reduction is also for visualization. So you can imagine trying to visualize a 100-dimension data set. It's impossible because you can't have a graph with 100 dimensions, right? So you reduce that down to 2 or 3 variables that you can show what your algorithm is doing. Because if you just have 100 dimensions, no one's going to be able to see what the output looks like. Okay, so we're going to do one method of feature selection, which is called variance threshold, and then we're going to do 2 methods of feature extraction. The first one is PCA and the second one is LDA. Just a heads up, LDA in general is a supervised learning technique used for classification, but the way that we're going to be using it today, you can use it as an unsupervised learning technique. This is also just to show you that every technique is not just specific to a specific type of algorithm type, if that makes sense. Your English was trash there. So you can use them for different things, and a lot of them tend to have overlaps between the different techniques. So classification, clustering, dimensionality reduction, and what is the other one? Regression. Right? There's a lot of overlaps along those 4. So first one is variance threshold. So as I said, feature selection, all you're doing is removing and adding columns from the original data set. Now in this case, the criteria to remove and add is based on variance. Okay? So variance, for those who don't know, is just the variability within a data set. So the more variation you have, the higher variance, and the less variation you have, the lower the variance. So in this case, variance threshold is you set a value for variance, whatever that value may be, for each column. And you determine the variance for each column, get the value, and if any one of those columns fall below the threshold, you just remove them. Okay. So That's just the formula for variance. That's just explanation. And then here's an example. So this is just a intuition example. There's no values. So let's say we have a public health data set, okay? And 96% of the individuals in the data set are all 36-year-old women. So now we know that 96% within the age column are 36, and 96% within the gender column are female. So you know for a fact, just based on that the variance in those two columns are going to be very low, right? Because you have 96% of one observation. So you can immediately remove those two columns because they're not going to make a huge difference when you algorithm, because there's not enough variability in those columns to make any impact. Does that make sense? Okay, so that's an example of variance threshold. Usually, when you're doing, when you're going through the full process of the data science, cycle, feature selection is not going to be the end of your dimensionality reduction. It's usually where you start, right? So you do your feature selection, and then you do something else. So you might go into PCA, you might push it into another algorithm, but you never just do this. This is not the end of your dimensionality reduction. It's always just the first step. Okay. All right. And then there's another method similar to variance threshold. I forgot to put the thing there. It's called correlation threshold. It's basically the same thing, but in this case, it's just a correlation instead of the variance. This is just giving the same thing. Understanding here with this example, let's say you have a data set that for real estate, and you have the size of the, let's say one of the columns says the floor area in feet and the other one is the floor area in square meters. So you can see it's identical, right? You just remove one and keep one because it's the same information. So that's correlation threshold. Now, I hope you guys enjoyed your linear algebra because you're going to be doing a lot of it now. PCA. Who here knows how to do principal component analysis? Who has done something along those lines? No one. Okay. Oh, there's someone. Oh, okay. Cool. Right. So basically, how PCA works is this is the first method that we're going to do of feature extraction. So what you're doing here essentially is you're transforming a data set into a new set of columns that represent all the columns. So you would set the number of columns you want to have at the end. You do your linear algebra, and you turn however many columns you start off with into 2 or 3 or 4 or whatever the case may be, right? And this is all based on linear dependence or linear independence and variance, right? So there's variance, so you all know what variance is now. Covariance is the same thing, but it's the relationship between, it's also taking into account the relationship between two different columns, okay? So just to show you an example of the variance and the linear dependence and independence, and as well as the covariance. So the first two lines, those one-dimensional lines over there, right? That shows examples of variance. So which one out of the two do you think has more variance? Anyone? You can even shout it out. X. Yes. Okay. So X has more variance because you have a higher spread of points across the timeline. Okay. So now, the bottom we have the covariance, and then the linear dependence and independence. Okay. So what you want to try and have when you're doing PCA is a high linear dependence. So you can see that the first one and the last one, they have a positive and negative linear dependence, which means the covariance between those two variables have a linear relationship. Okay, whether it's positive or negative, they have a linear relationship. And the one in the middle, there's no linear relationship at all. So when you do your covariance, you can think of it as plotting a two-dimensional graph, and you want to see how those two variables interact with each other. Okay, so here's the process that we follow to do PCA. So first you normalize your data, then calculate the covariance matrix, eigenvectors, eigenvalues, transformations, and then you select. Okay. So what I'm going to do is I'm going to show you the long method, then I'm going to show you the short method. The long method is very long. The short method is 2 lines of code. But if you want to understand how it works, that's why I'm going to the long method, because a lot of people tend to just take these things, throw them into the functions because it's just 1 or 2 lines of code, and they get output that they have no idea what it's trying to say or what it means. So it's always good whenever you're doing anything machine learning related to figure out how the long method works so that you actually know what's going on. Okay. So, covariance matrix. So all you're doing here is you're taking all your variables and you're working out the variance of those variables and the covariance with that variable and every other variable in your data set. So if we have a data set with A, B, C, and D, that's what your covariance matrix would look like. So across the main diagonal, you can see the variances, A, B, C, D, E, and on the sides of that, you can see all the covariances, okay? Okay, now once you have that, then you would calculate your eigenvectors and eigenvalues. I'm going to take you guys through an example. After this, I'm just going through the process. So, for those who don't know what eigenvectors and eigenvalues are, this is what they are. So, x is your vector, which would be your eigenvector, okay? So your eigenvector shows direction. It's a representation of direction within your plane, whatever the plane may be. Right, so now if you think of a 6-dimensional data set or 5-dimensional data set, which is what we have, every point within your data set can be represented by an eigenvector and an eigenvalue. Okay? The direction would be the vector, and the value would be the scalar multiplier of that vector. Okay, so the lambda over there, that's your eigenvalue. Does that make sense to everyone? Yes, it does. Okay, so to get your eigenvectors and eigenvalues, you just do normal linear algebra for those who've done it before. Just that formula over there. The determinant of A minus your lambda identity matrix equal to 0. Okay? And then you'll get your eigenvectors and eigenvalues. Then what you want to do is arrange them from highest to lowest in terms of the eigenvalues, and then that matrix or that set of values, those become the eigenvectors, and each eigenvector in that order are your new dimensions that you use for your new columns, right? They're called principal components. So the first one is the first principal component, the second one is the second, and so on. Okay. Let me go to the notebook. Okay. So, actually forgot I had variance threshold. So, just to show you guys the variance threshold, like I said, with most of these machine learning algorithms, you can pretty much do everything in 1 or 2 lines. So, as you can see here, there's a variance threshold formula. All you do is you take your data set, okay? So you guys can go through the variance threshold, it's pretty straightforward. What we're doing here is just giving what the data set looks like, which is here. Setting as a threshold value of 0.5, and then doing the variance threshold on the data set, and this is the output after you remove everything that is lower than 0.5. So you essentially end up removing one of the columns because it's 4, like I said. So that's all we're doing there. Now, PCA. So, as I said, the first thing you need to do is normalize your data set, right? So here we have a housing data set, okay? And what this housing data set is, it has distance to public transport, distance to shops, distance to hospitals, whether it's in a built-up area or not, what type of parking it has, the rainfall in the area, the category of the city that this property is in, and carpet, whatever that means. So now the first thing we need to do is, because we're doing PCA, we need to convert all the categorical data into numerical data. So we just use simple label encoder where we change the values from the categories to 0, 1, 2, 3. So you'll see here for the city category, we just made it category A is 1, category B is 2, category C is 3, and we do the same thing for the parking. Okay. And then we added those new encoded columns into the data set. You can see them over here. Right, and then here we normalize the data set. So you can see this is what it initially looked like over here, and this is the normalized form of it. Now this is where we go into all the linear algebra. So here's the covariance matrix, okay? And then we just use the simple formulas that Python gives us, and we get the eigenvectors and eigenvalues. So you can see here at the bottom, these eigenvalues are going from highest to lowest, right? And the eigenvectors that on top of those are the eigenvectors that correspond to those specific eigenvalues. So this vector corresponds to this value. This vector corresponds to this value, and so on. Okay? And then that's just a formula to get from here to here if you want to do the math yourself. And here we're just testing to see that the math was correct, and it says that it's correct, so cool. And last we do the transformation. Okay, so as I said, these are your eigenvalues in descending order. And now what we get at the end, after all the transformations, is your new dimensions for your new data set, right? The transformed data set. So essentially what we're doing here is we're transforming the x and y plane, if you think about it that way, right? So instead of having your normal x and y plane, you're going to have a new x and y plane. So it's going to have different dimensions based on the transformation you did in the PCA. Did everyone get that? No? Yes? Okay. So after we take the PCA of PCA 1 and PCA 2, which is your two new dimensions, or the two highest dimensions, this is the output of what that data set looks like using PCA. So this just tells us nothing, okay? It's just a blob of stuff. But I just wanted to show you the output in 2D, because we started off with the 4-dimensional data set, and now we're representing that same 4-dimensional data set in 2D without losing any information, because we still have every point that we had in 4 dimensions because of those transformations. And that's how we're not losing information. Okay. And then so you can see how long that process is. This is the short version. That's it. That's everything for the short version. That's all the code. All you do is just set the number of components you want at the end, call the function, and plot it. And you get the same output. So instead of having lines and lines and lines of code, you essentially just have 2 lines to do the PCA and then just some code to plot it. Okay? So obviously when you guys are doing your projects, it would be better to do this, because you don't want to waste time doing all the algebra yourself. But that's just there if you guys want to understand what's going on in the background. Cool. So, go back to the slides. Remember I was saying that we transform the actual axes themselves, right? So if you look at the first one, that's in terms of the direction of the data, V1 and V2, those are going to be your new dimensions. Okay? Because your first dimension is always in the direction of the highest variability. Remember that. The first dimension in PCA will always be in the direction of your highest variability. You might not always be able to see it because you might be working with a data set of 10, 20, 30, 40 variables, so you won't be able to plot that and see what it looks like. But just in this case, you have 2D, you can see that the variability is in the direction of V1, and then every corresponding dimension will always be orthogonal to that. It will always be 90 degrees. Okay, so basically like your X and your Y. And then the one on the right is what it looks like once it's transformed. This is after you do PCA. Okay. And then this is just what it looks like if you're going from a 3D space into a 2D space. So you see that we didn't lose any of the points. Every point that we had in 3D is still in 2D. It's just that we've taken the 2D, or the 3D, sorry, and transformed it into a 2D plane, so that we could represent the data in a way that's easier for us to understand. Okay, this method becomes very, what's the word? Helpful. I can't think of better English. When you have very big data sets and you're just trying to find what's the most important parts of those data sets. So if you're working with, like, let's say you want to do regressions to predict, I don't know, the price of your house one day. There's many variables you can use to predict what that may be, but you don't know what the most important ones are. And that's when you use something like PCA to cut it down, get the most important information out, and then take that and then do regression. So that's where I was saying how dimensionality reduction is always an intermediate step. It's always an exploratory step. And then you take that, push into another algorithm, and then get an answer out of that. Okay. Okay. And then this is just talking about the projection error. So the projection error is the direction that you select as your maximum variance direction. So you see here on the left, you could say that going across the x-axis might be the highest variation. Okay, it's a possibility. But the problem with choosing that direction is the points, the distance of each point from the line that you choose as your V1 essentially is very big. So you have a very high error when you do your transformation. So the points won't directly reflect the points in this plane once you do your transformation. Whereas in the other one, there is a projection error, but it's not as big as the first one. So you always want to try and minimize the projection error so that when you do a transformation, the new points are as close to your old points as possible. You can't avoid having an error, you always have one, but you need to make sure it's as small as possible. Okay. Okay. Cool. So this is the example that we went through in Notebook with the property, right? There's a data set that we looked at in the different categories, and we just went through it. This is, yeah. Okay. Okay, and then this is a plot. For those who've done PCA, what this shows you is you have something called a biplot. Okay, so generally when you do PCA, you don't actually know what variables you have at the end. So when you have PC1, PC2, PC3, etc., etc., you don't know what's in PC1. You don't know what's in PC2, and as you go, all you know is that you had 10 variables, and now you have 3. How you got from the 10 to the 3, you don't know. You don't know how much of column 1 is in PC1, or how much of column 7 is in PC3. You don't have that information. Okay? You can approximate how you got to that point by doing a biplot, which is where you plot every vector and then determine the distance of that vector between each axis. Right? It's a very long process. I don't know why you want to do that, but you can if you want to. Right? You don't need to know what's contributing, unless the question that someone's asking you is, what is the most important thing? Then you would have to do something like that. Okay? And then this is just going through the rest of the process. Okay, so LDA. As I said, LDA is generally a supervised learning technique. It's used for classification, but because of the way it works, it's also used for dimensionality reduction. So the example I'm going to show you here is we're going to do dimensionality reduction. YouTube is blank.
Yeah, I don't know why. It's showing. It's live. No, it's recording.
It's recording here. Try refresh, see what happens.
English.
Still nothing.
Yeah, it's nice. Let's see.